In this chapter, we will be exploring topics in set theory. In this lesson, we will be introducing the idea of a Venn diagram. And additionally, we will be using Venn diagrams to specifically look at intersection and union between sets.
Okay, so a Venn diagram here is a visual aid used to illustrate relationships between sets. And odds are really good that you have probably seen Venn diagrams before. They usually get introduced early in education in elementary school just because it's an easy way to look at relationships between objects. Usually, or maybe I should say to classify relationships between objects. So usually what we do here is we use a box again to represent our universe, and then we'll use circles to represent the different sets. Okay, and how those circles overlap, or if they do overlap or if they don't, that we use that to illustrate the relationships between the sets. Okay, now a couple of operations that we want to know about here. Intersection. Okay, well, intersection, when we talk about the intersection of two sets, that's a set all in itself here. Okay, this is an intersection is still a set. Okay, and what it is it's the set of elements that are common to two or more sets. So in this case right here, what I've drawn up here, this here would be the intersection between those two sets. Okay, the thing that is common to both, the group of objects that are considered part of both of those sets. We use this little upside down U to represent the intersection. And the way we would write that then is you'd write that A intersect B here. I've also heard it called A cap B. Okay, A cap B. And you'll see kind of why here in just a second, but A cap B. Now when we talk about it, when we refer to the intersection between sets here, it's the overlap between the two sets, and usually it's the word "and" that indicates intersection here. Because this particular set here, the objects here refer to both, they have the properties of set A and of set B. Okay, they have both together simultaneously. So that's what we mean by intersection here. Now, the other operation here is a union. Okay, and the union again is a set. Okay, we're going to have objects inside here. In this case, it's the set of all elements in two or more sets. So what it is here, it's not the ones that are necessarily common to both those sets, but it's the elements that are in those sets together. Okay, taken as a whole here. And we use this little U, this kind of stylized U, to represent the union. And you would write it as A union B, and I have seen or heard people refer to this as A cup B. So you've got A cap B, A cup B, whatever. Okay, but this is A union B. And typically what's happening here when we talk about union, it's the word or, okay, in its description here. So for example, if I've got, let's say, two sets here in my Venn diagram, A union B, if this is A and this is B, A union B would represent basically all of this. Okay, this is A union B. Now the reason I say it like that, or we draw it like that, is because if you pick any one particular element here, let's say you pick an element that's out here, okay, that particular element could be described as being in either A or B. A or B. Now it turns out it's specifically in A, but that's okay. If I'm only looking for elements that are in A or B, then that element qualifies. Okay? If I'm looking for this one right here, that element right there could be considered in either A or B. Now it's specifically in B, but it satisfies that statement. So does anything that's in both. Okay? So that's what we're describing here. A union B refers to all the elements in those two sets. Okay, all taken all together as a whole here. So, okay, now we're going to take a look at some specific questions.
In each of the following Venn diagrams, shade the region represented by the given set.
Okay, so this is saying A intersection B. I know that that's the part that's common to both. So A intersection B is going to be this set right here. This is set A. This little bit right here, this little kind of cookie shape here, this would be like only A. This section right here is going to be only B. Okay, so this is A and B together. So basically when I draw these two circles here, A consists of two parts, the only A and the piece that it shares with B. Okay. Now, A union B, okay, when you got the little cup there, this is going to be everything. Everything that belongs to either A or B. It's all good. So we shade the whole thing here. Okay. Now, A naught, okay, the complement of A. Now, where this gets confusing for people here is when you actually throw in the set B there, and they look at that and go, well, what about the B? Well, it doesn't say anything about the B. Okay, when we talk about A complement, B is irrelevant. It's absolutely irrelevant. A complement simply refers to everything that's not A. Okay? There's no mention of B in there. So that's going to be A complement. Okay, there's your circle representing A. Everything outside of it is A complement. Now, this gets a little bit more confusing when you throw a little bit more detail in here. So this is A intersection. Okay, so this is going to be where they overlap of not B. Not B. Okay, well, not B is going to be all this stuff outside here, outside of B. Okay, in fact, the best way to describe this here is, I'm going to just cover up B like this. There's B. Now, where does A intersect, or where does A overlap with not B? Well, where they overlap is going to be right here. Whoops. I just lost the pencil there. Where they're going to intersect here is going to be this part right here. Okay? In that little kind of cookie shape there with a bite out of it, that's only A. Now, where does not A intersect with B? Well, it's going to be the same sort of thing here. We're just basically flipping the names here. So again, if you cover up A, so not A is all around it. So where does that overlap with B? Well, right here. Okay. Now, finally, A union, not B. Oh, no, that's interesting. Now, this is A together with not B. So when we do this, what we're going to do here with union is you simply shade both sets. So first of all, we're going to shade A. And then we're going to shade not B. Now, where the question is going to come up with typically when we do a question like this, the question that arises is about this little part right here, the intersection, because it says, well, wait, it says not B, not B, that is B. How can you do that? Because this is a union. Okay, this is union. It's the set A together with the set not B here. Now, when I pick an element, I'm happy if it's in A, I'm happy if it's in not B. So if I pick an element here, that granted is in B, that's fine, but it is in A. It satisfies this part of the requirement here. That's fine. When we're talking union, it only needs to satisfy being in one of those two sets. It doesn't have to be in both of them, okay? Just one of them, okay? So that's why this is okay. Okay, I mean, if you want to think about it, if you're really stuck on it like that, then, well, this part out here, hey, this is not A. So how did this work? This is not A. Why did that fit? Well, because not A, I know this is not A, but it's also not B. And that's why, because it satisfied this part right here, that's why we shaded it. So really, when you got a union here, you're going to shade both of those sets. When you've got an intersection, you're going to shade the part that's common to both of those sets. Okay, I know, it takes a little bit of kind of playing with that to get that straight, but okay, believe me, you want to get that clear in your head as we move forward here.
At this point, we're going to introduce the concept of disjoint sets.
Okay, so now we're going to throw a little bit more vocabulary at you. Okay, disjoint. So we're going to have two or more sets have no elements in common. We call them disjoint. Okay, so this is a good example here, this Venn diagram, A and B here. There's no overlap between them. Okay, so in other words, you might want to say it like this: the intersection between A and B, A cap B, is the empty set. There is nothing that is contained between them. Okay, and when that's true, the union of those two sets, if you want to think about that now, actually this should say here the number of elements in the union between those two sets is equal to the sum of the elements in the two individual sets. Okay, if you just add up everything in here, add up everything in here, that's the same total as what's in both of those. And when that happens, we call these sets, another word that we use to describe them is we call them mutually exclusive. Okay? And you're going to see that this is something that's going to pop up in probability. Okay? We usually talk about events being mutually exclusive and whatnot. But this means the same idea. When we talk about mutually exclusive, we are referring to disjoint. We're talking about two sets that have no outcomes in common.
Match each of the following to the correct Venn diagrams represented below.
Okay, so we're going to be doing some matching here. Maybe what we do is let's take a look at the diagram here first of all. Let me zoom in a little bit here. Let's look at this diagram here. What have I highlighted here? Well, it's just A. Just A. So let's just take a quick look through here. Anything here that's just A. Ah, there it is. Yeah, just A. So this is going to be diagram 1. Diagram 2. Well, now that's interesting. Okay. What have we got here? We've got everything outside of A, including B here. Now, and I say including B because I'm also taking this chunk here. So this looks like not A union B. Okay, because I've got all of B highlighted and I've got all of outside of A highlighted. So not A union B, and there it is right there. Not A union B, so 2. Okay, 3. Well, that's interesting. Now, normally you would think that you'd have this highlighted inside here. This would be A union B. So this here has got to be A union B not. So another way to think about it is A union B, and we'll put a not there. So let's go up here. A union B. No, that's not it. Okay, here's a union, but that's not it. There's a union, but that's not it. Okay, so when I don't see the thing up there that I'm looking for here, there's got to be another way of thinking about this that could be equivalent to it. Well, okay, I'm shading outside of A, so it's like not A. But if it was just not A, I'd be circling through B. So it must be something like this. It must be like not A, and where that intersects with not B. And these two things will be equal here. Okay, not A and not B together, which would basically exclude everything inside A and B. So, oh, there it is. I popped right up to it. There's not A intersection not B. Good. All right. So this one right here, this looks like, well, it's just that little cookie thing. So this looks like where A maybe intersects with not B. Okay, where A intersects with not B. So let's take a quick look here. Oh, there it is, right? Number 1. A intersects with not B. 4. Now the number 5 here. Oh, I like that one. That's just B. So we'll go back up and look for where B is. Ah, there it is right there. So this is 5. Okay, now here's one I was looking for earlier here. Everything is shaded in A and B. Oh, this should be kind of labeled here, A and B. That's going to be A union B. A union, and there it is right there. A union B. This one here is quite clearly going to be A intersection B because it's the part here that's common to both. Okay, so where are we at here? No. A intersection B, no. Ah, there it is, A intersection B. So it's going to be 7 right there. All right, now this one's got a little squished here, but notice that everything's being shaded outside of B and A. So this is be like A union, not B. Now it wouldn't be intersection because if it was intersection, then it would just be that cookie cutter little, or that cookie piece there for A. So it's got to be A intersection, not B, or A union, not B. Okay, not there. Oh, right there, the last one here. A union, not B. This has got to be 8. Okay. 9. Look at what 9 is. 9 is basically everything outside of A. which is to me the easiest way to write that is not A. Oh, there we go, right there, not A. Oh, look at that. 10. Now look at this. What's in the middle here would be our A intersection B. And essentially what we've done is we've highlighted everything outside of that. So it's like A intersection B, not. So let's take a quick look. Well, it can't be, oh no, it's not that one. Those ones are all done. Okay, here we go. A intersection B, not. So here's my 10. Now, by default, I already know what 11's got to be because it's the last one here, but let's take a look at it. This is just that little kind of piece. Looks like it's got a cookie with a bite out of it, out of B. So this is going to be B, where B intersects outside of A. So B intersection, not A. And that's what I've got left over. There you go. Okay, whoops, let's just zoom out. Okay, so there we go. We've identified all of these different graphs here. Good.
Use the Venn diagram provided to identify the elements in the sets below.
Okay, so we're going to answer these questions by identifying what's in these sets based on this diagram right here. So we'll zoom in a bit so we can see this clearly. So here's the Venn diagram we're working with. First thing we want to find here is P. What's in P? Okay, so here's P. That's going to be 2, well, in order here. And I don't need to worry about order, but anyway, 2, 8, 9, 10. So P is going to have the elements 2, 8, 9, 10. Now we're looking at Q. Okay, Q is just going to be 7, 10, 29. 7, 10, 29. Now, P intersection Q. Okay, P cap Q. Okay, well that's this part right here, and there's only one element in it, that's the number 10. So P intersection Q is going to be the number 10. Now I could have basically gone up here and grabbed that from here. In fact, that might even be the more efficient way of doing this. So for example, when I say P union Q is simply going to be all of the elements in P and Q. Now, that's going to be from P, I get 2, 8, 9. Now, I'm going to get 10 from P as well. And again, that's in the overlap here. So now what do I get from Q? Well, I get a 7. The 10 is already there. I don't need to write it again. And then Q offers a 29. So there we go. 2, 8, 9, 10, 7, 29. Now, watch this as well. There's 1, 2, 3, 4, 5, 6 elements in P union Q. But in P, there's 1, 2, 3, 4, and in Q, there's 1, 2, 3. Now, altogether, that's 7, which is not what we get here. And the reason for that is because there's overlap. Because these two particular sets aren't disjoint. Okay, they're not mutually exclusive. They do share something in common. And so when you add them all up here, for example, when they're not disjoint, okay, when they're not disjoint, the number of elements in, let's say, P union Q is going to be the number of elements in P plus the number of elements in Q, and then we're going to subtract the number of elements in P intersection Q. Okay? Because we don't want to count those elements twice. Anyway, that's really not what this is about here, but it's just an interesting little side note because you can see it right now in this particular example. All right, not P. Okay, we'll probably have to go back to the diagram for not P. So outside of P, that's going to be, I got 11 and then 16, 7 and 29. So 7, 11, 16, 29. Here we go, not P. 7, 11, 16, 20, whoops, 29. Okay. Not Q. I got to go back here. Not Q is going to be everything outside of Q here, so it's going to be 11, 2, 9, 8, 16. Okay, so in order here, that was 2, 8, 9, 11, and 16. And again, order's not important, but it's hard not to, right? When you're listing numbers, it's hard not to. All right, not P intersection not Q, which it turns out is exactly the same as P union Q not. Okay, but it might even be easier to see it like this, P union Q not. Now, P union Q is going to be these two together. So what's not inside that? Well, 11 and 16. So this is going to be the set, whoops, 11 and 16. Here, P P naught union Q naught, which is, again, interesting that it's the exact same thing as P intersection Q naught. These are identical to each other. Now, these two have actually got, there's a name for these relationships here, and I can't remember what they are off the top of my head, but there's a name for that, the relationship between these two. But anyway, P intersection Q naught. Well, okay, here's P intersection Q right here, so I'm going to cover that up. There's P intersection Q, so not that. Well, not that is everything else. I mean, it's basically everything here except for the number 10. So that's going to be, what do we got here? 2, 7, 8, 9, 11, 16, 29. Whoops, oh, I'm sorry, you couldn't see any of those. 2, 7, 8, 9, 11, 16, 29. So everything here that's not inside that intersection between the two. P union Q naught. Okay, so P together with not Q. Now, not Q is everything outside of this. So essentially what that's going to include here is it's going to include P. So that'll be 2, 8, 9, 10. That's P. And then not Q is going to have 2, 9, 8, but it's also going to have 11 and 16. So I would include with this the 11 and 16. I don't have to double up on those things. P naught intersection Q. Okay, P naught, everything outside of P, so 11, 7, 29, 16. Where does that overlap with Q? Well, just at those two right there, 7 and 29. So P naught intersection Q will be just the two elements, 7 and 29.
Consider the set of prime numbers less than 20. If A is the set of numbers 3, 5, 7, 11, and 19, and B is the set of numbers 2, 3, 7, and 13, list the members of the following sets.
All right, so here we go. So we're only looking at prime numbers less than 20 here, okay? And look at the sets here. We got A and we got B here. And so now we're going to identify A and B, so A intersection B. And this is going to be, so what's in both of them? Well, 3 is in both A and B, yeah. Looks like 7, and that appears to be it, okay? Just the 3 and the 7 there, okay? A union B, well, this is an easy one. All we're going to do here is we're going to list off, first of all, everything that we see in A, and then whatever's left over in B. So there's a 2 in B, the 3 is dealt with, the 7's dealt with, and then the 13. Remember, order doesn't matter. Okay, order doesn't matter, so I don't need to write these in ascending order or anything like that. Not A. Okay, not A. Now we're talking about all the prime numbers less than 20. A is just 3, 5, 7, 11, and 19. Now, in this case here, it might actually help me to write these things out here. So I'm going to write the 3 and the 7 in the intersection. Now A is going to be 5, I got the 7, the 11 and the 19, and then out here in B there's an additional 2 and 13. Now let's think about all the prime numbers, because if they don't show up in here they got to be outside. So the prime numbers would be 2, 3, 5, 7, 11, 13. Now there should be a 17 out there, but the 17 doesn't show up anywhere. Now that should be all of them. 2, 3, 5, 7, I think about 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, there they go. So now, not A is going to be 2, 13, and 17. Okay? All the values that don't consist of, aren't inside A, so 2, 13, 17. Not A or B. Okay, not A or B. Well, okay, A or B, A union B, is everything here. So the only thing that's not in that group is going to be the 17. And then here, not A and B. Well, A and B is 3, 7. So outside of that, oh, well, there's a bunch here. 5, 11, 19. That's only A. There's the 2 and the 13. That's only B. And then there's the 17, which is outside of both of those. Okay, there you go. So filling in that Venn diagram is actually quite helpful in helping us see what's going on in that problem.
There are 30 students in a Math 20 class. Of those, 15 take English, 8 take music, and 5 take both English and music. Display this information on a Venn diagram.
Okay, now this question is not so much a question as it is just a demonstration. So we know we got 30 students in a Math 20 class, and we're told that 15 take English, 8 take music, and 5 take both. Now when you're told 5 take both, you want to start there. Okay, so we're going to write that in the overlap between English and music here. Now think about this. We know that 15 take English. That means 15 need to be in this circle right here. Part of that circle has already been dealt with. 5 deal with both. Now 15 are in the whole circle. The mistake that a lot of people make is they immediately just dump a 15 right here in English, but this circle consists of people that take only English and something else. Okay, so if you dump a 15 here, you're saying that 20 people take English, which isn't true here. I need the sum of these two numbers to be 15. So I gotta pay really close attention and not just immediately just dump the numbers in to these places here. For example, the other one here is 8 take music. Well, there are already 5 music takers accounted for, 5 in the center. So those 5 though also take English, so how many of them must be taking only music? And the answer is 3, so that the sum there is going to be 8. Okay, actually let's zoom in a little bit more there. Now additionally, we're told that there are 30 people in this Math 20 class. Now 10 and 5 is 15 and 3 is 18. That just takes into account 18 people. That means there must be 12 people who don't take either English or music in that particular Math 20 class. Okay, so the object is to fill in all these different regions here, but you really want to start in the center, and as you go out, you subtract from the groups that you're moving into. So for example, we knew this was 5, we moved into English, we knew there were 15 in English. Subtract 5 from that, that leaves you with 10 in this region that was left over. And that's how you want to work these problems through here. Start in the center if you can, work your way out by subtraction.
The diagram displays the number of students who are members of student council and the number of students who are members of the yearbook committee. How many students are on the following sets?
All right, so we're going to start off with how many students are on students council. Let's take a quick look here. There are 12 that are only on students council and 3 that are on both students council and yearbook. So that means there's a total of 15 on students council. There's a total of 15 in that circle. How many are on both students council and the yearbook committee? Okay, how many are on both? Well, that's the intersection of those two sets, and that is just that 3. How many are on the yearbook committee but not on students council? Okay, so basically are only on the yearbook committee, and that is this little shape right here, this little cookie cutter shape here, or cookie shape, 7. And how many are on students council or yearbook? Now when we say or yearbook, basically we're just saying how many people are just on committees here, and you're going to add up all these numbers here. So 7 and 3 is 10 and 12 is 22. Remember, or is that union. It refers to all of those different regions in there in those two circles.
There are 38 students in grade 12. The number of students in the drama club and the band club are shown in the Venn diagram below. Use the diagram to answer the questions about how many students are in the following sets.
Okay, similar question to the one that we just did. We're just interpreting the Venn diagram. So how many students are in both drama club and the band? Okay, are in both drama and the band. Okay, so here's drama, here's band. There are 8 that are in both. Okay, that's that intersection between the two of them. How many are in drama club but not in band? So only drama. And that's this section right here where it doesn't intersect, and that's 11. How many are in drama club? Okay, well that's that full circle. Okay, so 11 in only drama, 8 in drama and band, so altogether that's 19 in drama. How many are in band club only? Okay, well, again over here this is the band, and there's 6 right here that aren't part of that intersection, so that's 6 in band only. How many are in drama club or band club? Okay, so basically how many are in a club here? Well, that's everybody include in these three intervals, or sorry, three regions here. So 11 and 8, there's 19, and 6 is going to be 25. 25 people total. Now, how many are in neither drama club nor the band club? Oh, okay, well, wait a minute. How many people are supposed to be in this thing total? Well, according to the question, there should be 38 students in this universe here. Now, sometimes what we'll do is we'll put a little box up here, and I'll put a 38 in there to identify the total number of people in the universe. Now, in this case right here, we know that there's 25 people in that little group because we just answered that question there. So we're just going to take 25 away from 38. That's going to leave us with 13 people out here that aren't part of that particular group there. Okay, so there you go.
In a homeroom of 20 students, 15 take math, 12 take social, 10 take math and social. Fill in the Venn diagram and identify the number of students that take neither math nor social.
Okay, so now in this case here, again, 20 students total, so maybe we'll put the 20 out here. 15 take math. Now that's a total, so that's both these regions in the circle there. So I don't know what goes where first. 12 take social, 10 take math and social. So there we go. So 10 take math and social. There's 10 in that intersection between the two. Let's go back to the math here. 15 take math, so that means there must be 5 here that take just math. If 12 take social, there must be 2 here that take just social. Now, putting that all together, 5, 10 is 15. 2 more students gives me 17 students. Now, there should be 20 total, which means there must be 3 out here that don't take either. And that's what they're being asked for right here. How many students take neither math nor social? 3.
All the students in a class of 35 takes physics or chemistry, or both. 29 take chemistry, and 15 take physics. Fill in the Venn diagram and determine how many take both.
All right, now this question requires us to be a little bit more clever here. Now, we're told that 35 students take physics or chemistry. So in between these two circles here, there's 35 students, okay? So P union C, the number of students in that little group there is 35. Now, we know that 29 take chemistry and 15 take physics. Now, if you add that together, okay, 29 and 15, we're getting 44. Now that's substantially larger than that. So the number in physics plus the number in chemistry is going to be 44. Well, that's substantially larger than that. Okay? So now let's think about this. And we saw this before. The number of students in physics or chemistry is going to be the number of students in physics plus the number of students in chemistry minus the number of students in physics and chemistry. Well, that's the part right now that I don't know. So I'm going to bring this over and solve. The number of students in physics and chemistry is going to be the number of students in physics plus the number of students in chemistry minus the number of students in either physics or chemistry. And that's going to be physics and chemistry is going to add together to get 44. And if we subtract 35 from that, we're going to get 9. Now that actually makes a lot of sense here, because if you think about it, I'm expecting 35 as a total between these guys. I'm getting 44. I'm sorry. I'm getting 44 when I add what's in physics and chemistry. But that's because I'm adding this group twice. So now, how much bigger? 35. How much bigger is 44 than 35? 9. So what's happened here is I've doubled up on 9 students. Now, take that 9 away from the ones who take chemistry, and you're left with, I put that in the wrong spot. Chemistry's over here. 29 take chemistry, 9 take both, 20 take chemistry. If 15 take physics, 9 take both, that leaves me with 6 that just take physics. And then this question is asking specifically how many take both? 9 take both.
Of the students in grade 11 at a certain high school, 76 are enrolled in physical education, 24 are enrolled in music, and 10 are enrolled in both physical education and music. There are 15 students in grade 11 who are not enrolled in physical education or music. Identify the number in the following sets.
Okay, so in this question we're given a whole bunch of information here. So we're told, actually let's go to this diagram here. We are told that we've got 10 enrolled in both physical education and in music. So that's 10 right there. Then we're told that 24 are enrolled in music, which would mean that there are 14 that are in just music. So that the total in this circle between those two is now 24. 76 are enrolled in physical education, which means there are 66 enrolled in just physical education, so that the total here between those two is 76. Okay, so that the total number in phys ed here is 76. Now, there are 15 who are not enrolled in physical education or music, so they're out here. Okay? Now, the first question here is how many students are in grade 11? Okay, well that's going to be the sum of all of those numbers there. So 66 and 10 is going to be 56. And then if we, 14 and, 56, 76 is what I meant to say. 66 and 10 is 76. 14 and 19 is 29. Add those together, you get 105. So there's a total of 105 students. Now, what percentage of students took music only? Well, based on the diagram here, 14 took music only out of 105 students. So let's do that on our calculator here. I got one just over here, hold on. So 14 divided by 105 is going to be 0.13 repeating. So we're talking about 13% roughly. Approximately 13% took just music.
In a class of 20 students, there are 13 students who play hockey and 12 students who play soccer. 4 of the students do not play hockey or soccer. How many students do play both hockey and soccer?
Okay, now in this case here, you're not told how many students are in the overlap between the two. That's what you're looking for here. However, we do know that 4 students don't play either one. So 4 students are out here. Now, what that means here is in a group where there's supposed to be 20 students total in the universe here, that the number that should be here in this total here should be 16. In the union between hockey and soccer should be 16. But if I add the 13 who play hockey to the 12 who play soccer here, I'm getting 25 students. Okay, so when I add, and again here, if I take the number of students that should be in the union between hockey and soccer, okay, this is going to be the number who take hockey plus the number who take soccer minus the number that's in the overlap between the two. And really what I want to do is I want to figure this out here. Now, I know that this number should be 16. Okay, based on my Venn diagram right now, 20 people total, 4 who don't take either. So the combined total there should be 16. However, we know that there are 13 who play hockey and 12 who play soccer. So the question is, how many are playing both? Okay, well now we're just going to solve this. So I'm anticipating where this is going. So that's 16 is equal to, well, that's going to be 25. And if I bring that over, this will be the number in hockey and soccer will be 25 minus 16. And I think most of you probably recognize that pattern of numbers here. That's going to be 9. So, how many students do play hockey and soccer? Well, we've just figured out that's going to be 9 right there. Now, we might as well fill in the rest of this. If 9 are in the overlap and 13 play hockey, that means there's got to be 4 here that play just hockey. And if there are 9 here and 12 who play soccer, there must be 3 here that play just soccer. So to answer the question specifically, how many play hockey and soccer? 9.